Hello, welcome to the video over piecewise graphing notes. So today we're going to talk about piecewise function. Now, the reason that we call them piecewise functions is because you're taking a bunch of different types of functions and putting them together into one. And it might not always be as smooth or as nice looking as some of the functions that we've dealt with so far this year. So for instance, just looking at this first function, right, you can see it's jagged, it comes to points, and there are holes and things going on. And so there's two types of problems that I'm going to ask you when it comes to graphing. One of them is to be given a graph and write the equation. So you have to come up with the equation or the rule that represents this graph that you see. The other option is for me to give you an equation and then you draw the graph. So let's go through both. Well, if we want to write a rule for the function shown below, this one on the left, the first thing I want to do is break it up into its respective pieces. Now, when I break it up into pieces, I want those pieces to make sense. So anytime it's consistently something and then breaks, right? So there's a drastic change. The change is where I'm going to put it's where I'm going to piece it. So for instance, if I go from -6 to -4 here, well, that's a constant function at 2 to the left of that. And so I'm going to put my break right here at -4. Because as I go to the right of -4, it's no longer just constant, which means I want to use a different equation to represent what's going on here. Now, as you continue to go to the right, it's still that decreasing linear function until you get to 2. Right, and I'm talking about the x equals 2. Once you get to 2, it goes up again. And I could find an equation that represents that so that I don't have so many pieces, but because we're dealing with pieces, we might as well. So I'm going to break it right there. Alright, so I've got 3 different pieces going on. Now when I write my piecewise function, it's going to be f of x. Right, and you can call it whatever of x you'd like. And then braces. And those braces are going to represent your pieces. Now when you have your pieces, you have to write the equation for that piece, a comma, and then the domain where that piece exists. So for instance, and you always go from left to right. So for instance, I'm starting over on the left side. So where x is less than -4. So I'm going to start by actually writing my domain. Actually, all of my domains. The next piece is between -4 and 2. Now, you also have to look and see this point right here. Right? On the breaks, is it open or closed? And so, because these are open, we are not going to use or equal to symbols. We're just going to use our less than symbols. So from -4, less than x, which is less than 2. And then the last piece is where x is greater than 2, because it's to the right. And so x is greater than 2. My next job is to write the actual equations. Now when you have a constant function, like you do in this left area right here, that is always going to be 2. No matter where you are, the y value is always going to be 2, no matter what x value you're talking about, from -4 to -infinity. So the equation is just 2, which actually makes that really nice. Now let's talk about this middle piece right here. Well, I know how to write a linear equation, right? Y equals mx plus b, where m is the slope and b is the y-intercept. So first, let's find the slope. Well, slope is given to you by rise over run. Well, let's see. If I start here, and I go down and over, down and over. That means it's down 1, right 1, down 1, right 1, down 1, right 1. Okay, well because it's down 1, right 1, that means the slope is just -1, right? Because it's down, rise, which is -1, over 1. Now we have the y-intercept. Well, the y-intercept for this is going to be right here. So that's at -2. Well, if y equals mx plus b, then y will equal m, which is -1, x, plus our b, which was -2. And there's the equation. Now let's find this last piece. I'm going to do it in a very similar manner. First, I'm going to try to anticipate, well, okay, let's find our slope first. Sorry, slope. Well, if I start here, I go up 1 over 1, up 1 over 1, up 1 over 1 to get to the next point. So it's positive 1, and the y-intercept. Now, this doesn't actually cross the x-axis, but if I imagine it continuing, it would cross right here. So that would be at -6. So the slope is 1, so it's just x, and then the y-intercept is -6, so it's x minus 6. And there's your piecewise function. It defines everywhere you want to go. Let's do another one. Now on this one on the right, you can see that the pieces aren't actually together. They're not all together. And so when you find your pieces, we're going to cut the graph where the breaks are. So for instance, right here, right, because we're going from one function to another. So at -4, and then right here at 0. So when we write our equation, our first domain is going to be to the left of -4. So x is less than -4. Our middle domain is going to be between -4 and 0. And then our right domain is going to be from 0 to infinity, so where x is greater than 0. Now, on this graph, you see these points right here? Those are closed circles. So because they're closed, we need to have an or equal to somewhere. The question might then be, well, which domain has the closed circles? Well, it's the middle one because that's connected to the middle graph. So because this line in the middle is connected to the closed points, we're going to put the or equal to's under those, right, for that part of the domain, for that middle portion. And now we write our equations. So let's start over here. Well, always start on the left, right? I like to start from left to right. So this is always going to be 0, right? That's what it is. So it's just 0. Right, because it's constantly 0. It's a constant function. All right, let's find the middle one. So we have rise over run, rise over run, rise over run, up 1 over 1, up 1 over 1. And so because it's up 1 over 1, the slope is 1. So slope is 1. Now let's find the y-intercept. Well, hey, look, I already circled the y-intercept, coincidentally. Right, so the y-intercept is 0, which makes this equation 1x. So it's just x. Now let's look at this piece over here. So we've got this downwards looking parabola. That is a parabola. So that means that it's going to be ax squared plus bx plus c, potentially, right? And we can write it however we want, and as long as it represents what's going on here. Now if you look at this graph, it is opening down. So opens down and is moved up 4 spaces. And I know that because normally a parabola, a quadratic function, would start at 0, 0. This one doesn't. This one starts at 0, 4. And so because I know these two things, if it's opening down, that means it's negative. And if it's up 4, that means it would be plus 4. That is why the equation is -x squared plus 4. And there you go. Those are your equations. Now, the second type of problem that I could ask you to do is to try to graph a function, right? The actual function. And so this time we're going backwards. Instead of them giving us the equation, or I'm sorry, the graph, we have to come up with the equation. They give us the equation. We have to come up with the graph, which is not so bad, right? The first thing I would suggest you do is look at where you're changing from one equation to another, and that's going to be given by your domain, which is right here and right here, right? So because we're dealing with 2, I'm going to draw this imaginary vertical line at 2, right? And I'm going to make it dotted. Oops, that's not 2. That's 3. I'm going to make it dotted because it's not actually part of our graph. It's just going to be a guideline that tells me, oh, that top equation is to the left, and then the bottom equation is to the right. And I know the top equation is to the left is because it's x is less than or equal to 2. And I know the bottom equation is to the right because it's greater than 2. So now, I'm going to graph what I know about linear functions because they're both linear. Well, if it's negative 2x minus 1, that means the y-intercept is at negative 1. So let's go to negative 1. And then it's going to be down 2 over 1. So down 2 over 1. Down 2 over 1. Now, this is or equal to, so that's going to be a closed point. And then I'm going to take my straight edge that's that you can have nice and handy and draw that function. Okay? And that would keep going forever and ever and ever. Now to the right, I have the equation negative x plus 4. So let's go to negative x plus 4. Let's try to graph it. Right? The y-intercept would be 4. So theoretically, I'd be right here. Right? Except that that's not in the domain. So I'm not going to actually include that as part of my graph. I might use it as a guideline though. Now I know my slope is negative 1 because it's negative x. So it's down 1, right 1. So the next point would be here. Down 1, right 1, here. Down 1, right 1, here. Down, and keep going. Right? Except that I'm only going to use the points to the right of this dotted red line. And this is greater than 2. Right? Not greater than or equal to 2. Which means that that is going to be an open circle. And then go on from there with my straight edge because I'm using a straight edge. And then just erase that part. And there's my graph. Now it's asking me two more things. It says first determine whether or not the function is continuous. Now what does it mean for something to be continuous? Well, what it means is that when I draw the function, I don't have to pick up my pencil. Okay? If I go from left to right, I never have to lift my pencil. That's the simple way of thinking about continuity, or whether or not the function is continuous. So, let me draw this function one more time, and I'll use green. Let me draw, lift. Draw. So because I lifted my pen, this is not continuous. So the answer for continuous, is no. No, because I had to lift my pen. Then it asks us to find the domain and range. Now, domain and range are something that we've talked about before, right? Domain is always left to right, range is bottom to top. So if I go all the way to the left, does the function exist, right? Does it keep going to the left? Yes. Does it keep going to the right? Yes. The only place where it might not be defined is when it touches that red vertical line, that place where it switches from one equation to another. Here, this function is defined. So because it has a value, this function has a domain of all real numbers, or negative infinity to positive infinity. Range is bottom to top. It goes down forever because of this. It goes up forever because of this. And it does, it does exist at 2 as well. So, that is also negative infinity to positive infinity. And that's how you graph them and answer all those questions. So let's do a couple more, right? Maybe 4 more after number 2. All right, let's look at where we're dividing this function up. We have negative 2 and positive 2. Now I know that because if you look at your domains over here, that's supposed to be a star. We're dealing with x is less than or equal to negative 2. Negative 2 is less than x, which is less than 2, and x is greater than or equal to 2. So that's where I'm going to draw my vertical lines. And I'm just going to make them dotted. So negative 2, positive 2. Okay, now I can start drawing. Now I know that y is equal to negative 4 when x is less than or equal to negative 2. So this first one, this first one right here is at negative 4. Y is negative 4. It is or equal to, right, because of this, which means it's a closed dot at negative 4. And it's constantly negative 4. So that'll just be a straight horizontal line. Easy enough. Okay, x minus 2. Now notice, neither of these are or equal to, so they should both be open circles. So let's go ahead and draw that. So we have the y-intercept is negative 2. Well, that's here. And our slope is 1, because it's 1x. So it'd be up 1 over 1, up 1 over 1. Oh, that's on the line, so that's a circle. That's an open circle. Down 1, left 1, down 1, left 1. Now, that would also be an open circle, except that it's already filled in by another function. So I'm going to connect the dots. All right, there's that second function. Last function, negative 2x plus 4. Well, that means we're starting at y, the y-intercept is 4, so I'm going to have this, pretend that's there, right? Down 2, right 1. Down 2, right 1. Okay, that's where our graph actually starts, because that's in that domain. Down 2, right 1, down 2, right 1, down 2, right 1, down 2, right 1, right? And it'll keep going forever and ever and ever. So, bam. Okay, let's get rid of those, because those aren't actually on our graph. And now we answer the other two things. So is this continuous? Did I have to lift my pen as I move from left to right? Well, let's try it. Don't have to lift. Don't have to lift. And don't have to lift, and that'll go on forever and ever. So is this continuous? Yes. Let's look at the domain. Well, if I go from left to right, it's continuous. All the numbers are included. So the domain is actually negative infinity to positive infinity again. Now the range is interesting because range is bottom to top. How far down does this function go? Well, according to that arrow, it goes down forever, so negative infinity. But the highest y value is right here. Okay, and it's actually on the x-axis. So it actually ends up being 0. That is a closed point because we drew it closed, because we knew to do it that way. So it gets a bracket. I know this video was a little bit long. I just wanted to make sure you understood it completely. And these are the easy problems. If you'd like more help and more instruction, I've got another video that you can watch. You do not have to watch it, but I find it very, very helpful just to have extra examples. So if you need extra examples, go watch it. Have a good day.